Sydney, I need your help.
What? What's up?
Last night, my basketball was fine. I was playing, and it was fully pumped up. And then I left it outside last night, and now, look, it doesn't even work. Do you know what happened?
That's very peculiar, but I think I can probably explain it to you with my ABET certified chemical engineering curriculum. All right, let's get started, Kat. So, let's start off with just stating your problem. We have, at room temperature, which is 25 degrees Celsius, your basketball is fully pumped with a volume of 7.014 liters and a pressure of 0.51 atm. You left it outside last night and the temperature dropped to 0 degrees Celsius. Your ball is flat. So when you went to go get the ball, you noticed that it didn't bounce as well, right? So what I'm thinking is that you have a new pressure in your basketball. So let's start to solve this problem. The best way and the most accurate way to solve this is probably using the SRK equation. So here we have our pressure, which is equal to our gas constant times temperature over V minus B, which you use over here, and you find the critical temperature and pressure to find B over here. And then you also have
Stop. I have no idea what you're saying right now.
I can explain it to you.
No. I need something simpler. Can you talk to me like I'm 10?
Okay, I got you. Okay, so instead of that, we have something a lot more simpler. All right, we have the
A lot
Van der
more
Waals.
simpler?
Yeah, a lot more simpler. We have the Van der Waals equation, okay? So this case, like it still has like a lot of, it's kind of precise, right? So you have like your A and B values, which you look up into a table, and then you have like your pressure.
Wait, what is A and B? What is A and B?
A and B, it does like the intermolecular forces and everything like that.
Nope. No. I don't have any tables. I don't care about the tables. I just want to know the new pressure in my basketball. So could you talk to me like I'm 5, please?
5
years old.
I got you. Okay, so what we have here is the ideal gas equation. So we just have, which is commonly known as PEV-NERT. PV equals nRT, okay? So you got your pressure, your volume, your moles, your gas constant, and your temperature, all right?
Okay. Yeah.
All right, so when we're talking about PEV-NERT, or the ideal gas law, first we need to make a few assumptions. Our first assumption is that gas molecules have negligible volume. Do you know what that means?
Yeah, it means that we don't really count the volume of the air molecules. Oh, and that makes sense because there's so much volume in here that those definitely don't take up much space.
Exactly. Like an actual mole of like an air gas is so small that it doesn't even really matter.
Okay, yeah.
So then the next one is that molecules exert no force on each other. Do you know what that means?
Yeah, but it doesn't really make sense because isn't there like always attractive and repulsive forces between molecules?
Well, yes, but in the ideal gas law, we're assuming that these molecules do not actually exert a force on one each other because it's just so negligible.
Okay, so very small force.
Right, which is negligible. And then our third assumption is that collisions are elastic. Do you know what that means?
Oh yeah, that means that there's no kinetic energy lost in the collisions when the molecules collide with each other or when they collide with the wall of the basketball.
Right. So if I just like threw this pen at this, it should bounce back at the same velocity, right?
If it were an ideal gas.
Exactly. All right, and then for the last one, it works best at high temperature and low pressure.
Well, I know that 0.51 ATMs is a low pressure because like atmospheric pressure is 1 ATM. But can you explain the high temperature one to me? Because 0 degrees Celsius is pretty cold.
Yeah, well, if you're just thinking if you're going to walk outside in some shorts and flip-flops, yeah, 0 degrees Celsius is kind of cold. But in the grand scheme of things, if you think that 0 degrees Kelvin or negative 273 degrees Celsius is absolute zero, and 0 degrees Celsius, which is where you left your ball outside, would be 273 degrees, that in compare is a pretty high temperature. And then also, STP is 0 degrees Celsius and 1 ATM. And STP is kind of the range that you're looking for an ideal gas.
Oh, okay. So can we solve the problem now?
Of course we can! Okay, Okay, Kat, you ready to solve this?
Ready.
Okay, all right. So here's what we already know. You have your initial pressure, which is 0.51 atm. You have your volume, which is going to stay constant, and that is 7.014 liters. You have your gas constant, which is going to stay constant because it's a gas constant at 0.08206. And the units for this are liters, atmospheres over Kelvin mole. So don't forget your units, all right? And then you have your initial temperature. You want your ball inside was 25 degrees Celsius, and to convert it to Kelvin, you need to add 273. The first portion of this is that we need to solve for moles because we don't know how many moles of gas are currently in your ball. So let's go over here, and I solved it for you. So using PV equals nRT, we're going to solve for N. So we're just going to divide both sides by RT. And over here, what we get after we plug in all of these values is 0.146 moles. So using that, we're going to find your new pressure. We know that your new temperature is 0 degrees Celsius because that's the temperature that you left your ball outside, sorry. And we're gonna also add 273 degrees to that as well. So you're gonna have 273 degrees Kelvin. And that's pretty much the only thing that changes besides your pressure of your ball. And what we're gonna do is divide both sides by V, and you have nRT over V. And then we're just gonna plug in all of these values, and you're solving for ATM, and this is your new pressure. So now the pressure of your ball is 0.467 ATM, and the initial pressure of your ball was 0.511 ATM. So there was a decrease in pressure, which pretty much proves why your ball's flat.
Oh, okay. So let me get this straight. You can only have one unknown to solve for in the ideal gas equation at once. So what you did was you used the initial conditions and you solved for N.
Mm-hmm.
And you had to do that because in the final conditions, we didn't know P and we didn't know N. But then, since you got to plug in N, we could solve for the final pressure.
Yeah, that's exactly what I did. You
So
read my mind.
I just have to pump up my ball, basically.
Yeah, go pump up your ball, Kat.
Okay, thanks, Sydney.
Pump it up.